Do you guys remember the activity that we opened up this chapter with? Me making free throws and how amazing I am as a free throw shooter. I am an 80% free throw shooter. I haven't been able to back this up yet, but I'm an 80% free throw shooter. I've decided to take another simple random sample of 50 free throws to try to prove myself now. So I want to write down what the hypotheses should be, and I want to define the parameter of interest here. What would the null hypothesis be? P equals 0.80. Yes. What would the alternative hypothesis be? Yeah. P is less than 0.80. And in this case, what does P mean? Yes, the proportion of free throws that I make. Make sure, by the way, when you're writing your parameter, don't use past tense language. Remember, we're always using this to try to talk about something that we don't know. And if you're using past tense, it's already happened. We already know it. I know how I did on my previous simple random sample of 50 free throws, but that doesn't necessarily tell me how I'm going to do on the next one, or the one after that, or how I'm going to do in the long run. Yesterday we talked about the types of errors. Which type of error was it where we rejected a null that was actually true? That's a type 1. Where we reject a null that's actually true is a type 1 error. So what's a type 2 error? Failing to reject when it's really the ha that's true, when it's really the alternative hypothesis that's true, but not finding enough evidence, not finding convincing evidence to reject the null hypothesis. So what would a type 2 error look like in this situation? Yes, it's where the true proportion of free throw makes for me is actually less than 80%, but we don't find convincing evidence to say that. I'm a less than 80% free throw shooter, but we fail to find convincing evidence that I'm less than an 80% free throw shooter. Thank you. All right. So yesterday, when we talked about the type 1 and type 2 errors, we will always know what the probability of making a type 1 error is. Yesterday we said the probability of a type 1 error is the same as what? Same as our significance level, same as our alpha level. So whatever alpha level we choose, we are basically owning that we have that much of a probability of making a type 1 error. We didn't talk about the probability of making a type 2 error. And that's what we're going to investigate today. So this is where you're going to need your devices. You can either type in the website that's on the page, or there's a link on Canvas if you want to hop over to Canvas. Right here, this is on today's page, so on the Wednesday 129 Power of a Test, you can click on this link right here, or you can just type it in. But this is where we're headed. Should bring up a screen that looks like this. All right. So as you guys are getting there, number 3 says, suppose that Ms. Bolt's true free throw percentage is actually 66%, which would mean the ha is true, right? Because that's less than 80%. So if my true free throw percentage is actually 66%, we're going to enter this information into that website. And we're going to click on the display type 2 error, and it's going to show us a blue shaded region that is the probability of making a type 2 error. So let's hop over here. The null hypothesis value. What is our null hypothesis? P is equal to 0.80, so take this slider over to 0.80. What are we saying the actual true value for P is? Yeah, we're saying that it's 0.66, so I'm going to take this slider over to 0.66. Okay. Is our sample size okay? Is N okay? Yeah, because we said we're going to do a simple random sample of 50 free throws. And did we write our hypothesis as a one-tailed or a two-tailed test? One-tailed. What would it look like if it was a two-tailed test? What would I see that's different? How would my alternative hypothesis look different? Does not equal. So if I had not equal to 80, then it would be a two-tailed test. But we just wrote less than 80, right? Less than 0.80. So up here where it says alternative hypothesis, I don't want a two-sided test. I want which one? I want the less. So far, so good? All right, we're going to display the type 2 error. So this checkbox right here. Go ahead and click that on your screen after you've made sure that everything else is the same as mine. And this is what you should see. And if you look on your page, it has this picture right there printed for you, correct? You're welcome. I didn't think you would want to sketch it. This blue shaded region is the probability of a type 2 error. And if you look up at the top, it tells you specifically, not just from shading, but it gives you a percentage, the probability of making a type 2 error. What is the probability of making a type 2 error? 24%. So let's write that down. This is our probability of a type 2 error. So if we don't make a type 2 error, we don't make a type 1 error, then we've made a correct decision, right? And in this case, we started off with this idea that I'm actually a 66% free throw shooter, even though I'm claiming to be an 80%. The truth is that I'm a 66% free throw shooter. So the alternative hypothesis is true. This is the probability that I screw it up. So what's the probability that a correct decision is reached? 76%. How did you do that? Yeah, 1 minus this to get this. This right here is called the power. And the probability of a type 2 error plus the power will always equal 1. Power is the probability of a correct decision. Right. So I want to write this, and then I want to go back and look here. When we're talking about power, for power, we have to have a specific value for the alternative hypothesis. When we're talking about power, it's not just P is less than 0.80 or P is greater than 0.80 or P is not equal to 180. We have to have an actual number that we think for our alternative. In this case, the alternative hypothesis is that P is equal to 0.66. want to take this right here and interpret what that means in context. It says, if the ha is true. What was the ha again? Remember, we had to change it from less than 0.80 to this. What's that mean? What does P equals 0.66 mean here? Yeah, that I'm actually a 66% free throw shooter. So if I'm actually a 66% free throw shooter, this is the probability right here, 76% probability of correctly finding convincing evidence for the alternative hypothesis. If I'm actually a 66% free throw shooter, there's a 0.76 probability that the significance test will find convincing evidence to reject the null, that I'm actually an 80% free throw shooter. We're going to add some stuff to this picture here. So this curve in the picture that's printed on your notes, the curve that is to the right, this is the normal curve, the normal distribution, if the HO is actually true. If the null hypothesis is true, this is what the population distribution would look like. And if the alternative hypothesis is true, that's represented by this smaller, or at least slightly shorter and more spread out normal curve. That's my alternative hypothesis. This shaded region right here, that is the probability of a type 2 error. The power is this region here. Our null hypothesis was that P equals 0.80. The alternative hypothesis is that it's actually 0.66. And if that's the truth, then we have a 76% probability of reaching a correct decision here, of finding convincing evidence that the HA is true. There's one other thing that I want to show you on the website, and then I'm going to let you guys loose to explore number 4 on your own. All right, so looking at this picture, I'm going to have this display the power for us. So the blue is the probability of a type 2 error. The green is the power. I want to see. We're going to show the critical values and the rejection region. So right here, this would be the cutoff. If I was drawing my normal curve, that's why that's the line in between my type 2 error and my power. This and over on the red curve is where we would be rejecting. That's why it's part of the power, because I would be rejecting the null at that point. I would like to give you guys a little bit of time. You need to make sure that the power is displayed. You do not have to look at both the power and the type 2. I want you focused mainly on the power. And I want you to see how you could adjust the sample size, the alpha level, or the alternative value for P, so in this case the true value of P, to increase the power. I'm going to give you guys about 5-6 minutes to play around with N, alpha, and P to see what you need to do to increase the power. Write down your observations. Only play with one thing at a time, and write down what your observations are. What do you do that increases the power? How would you change N to increase the power? Increase N, yes. Increase N. Let's go look at the picture. So I'm going to turn off my type 2 error. I just want to look at my power and my rejection region. If we take N up, what does it do to both of my curves? What'd you say? It decreases the variability, which is another way to say they get narrower, right? Decreases our variability. lower variability in both the distributions means that the overlap, that overlap is my probability of a type 2 error, that overlapping space becomes less. What can we do to the alpha level to increase the power? Increase the alpha level. I'm going to go look at the picture here. All right, so increasing n makes it narrower, which makes my overlap space smaller. I'm going to take n back to 50. Oops, I don't want to do that. I want you to stay at 0.66. And I want you to go back to 50. All right. Alpha level. What changes when the alpha level gets bigger? What's changing? The shading is changing because what's moving? This line right here is moving, right? That line is where we would reject or fail to reject. That's the cutoff for reject or fail to reject. So increasing the alpha level, power requires us to reject the null. Increasing the alpha level increases the probability that we reject the null. If we increase the alpha level, we increase the probability of rejecting the null. And then finally, we have this alternative value for P, which on here, the alternative value for P, they're calling the true value of P. What would you do to that alternative value of P if you wanted to increase the power? If I take it over here, does that increase my power? My shading went away entirely. Does that have higher power or lower power? That's lower than I was at 0.66. 0.66 looked like this. What about if we take it down here? So what am I doing to increase the power? In this case, I'm decreasing it, but what about if I was actually a way better than 80% free throw shooter? If this true distribution was actually over on this side, if that's what my original alternative hypothesis was, I want the distance between my null hypothesis and my alternative P to be larger. It could be on the negative side. In this case, I'm making it smaller. But if my alternative hypothesis had been written with a greater than instead of a less than, then I want it on the other side. So it's not that we always make it smaller, we make it farther away. Farther away from decreasing P, we increase the distance. Absolutely. Thank you. Making the value for the alternative hypothesis farther away from the null hypothesis will increase the power of the test. Let's flip this over and look at our big takeaways. So here's that same little two-way table that we made yesterday. Rejecting the null when the alternative is true. We had a smiley face there yesterday. That is our power. The probability of a type 2 error plus the power equals 1. So if I want to know the probability of a type 2 error and I know the power, I can subtract those to find the probability of a type 2 error. Interpreting the power, if the ha is true, and then you have to give a specific value in context. In this case, we were using, I'm actually a 66% free throw shooter. If the ha is true, there is a, whatever my power is, probability of finding convincing evidence to reject the null. And then these are the three ways to increase the power. I would like for you guys to do the check your understanding. There are 3 questions there, although that very last question has 2 pieces to it. Let's see if we're done in 5-6 minutes. If we need a couple minutes after that, I can add some more time on, but let's see where we're at in about 5 minutes. Disk 4 right here, and you just need to put your phone in one of those pockets right there. Oh, yep. Thank you. Don't forget your phone. in number 1, it says, suppose the true proportion of invited guests that will attend the party is actually 0.70. Then the power of the given significance test is 0.10. Interpret the power. Given that sentence frame up at the top, how would we interpret the power here? What does it mean right here? What's that 0.70 mean? The ha, what is the ha in this case? Like, I know it's 0.70, but like, what do we mean? We're saying that that's actually the true proportion. So if the true proportion of invited guests that are going to attend is actually 0.70, yes, so we would have a 10% probability or a 0.10 probability of finding convincing evidence to reject the null. The power is the power to reject the null. That's the probability of us rejecting the null if the alternative hypothesis is actually true. If the true proportion of all invited guests that will attend the party is 0.70, then there is a 0.10, that's our power, probability of finding convincing evidence to reject the null that 75% of guests will show up. Okay, so working off of what we did in part 1, not part A, I should say 1. What's the probability of a type 1 error? 0.05. Probability of a type 1 error is whatever my alpha level is. How do we find the probability for a type 2? Subtract the power from what? From 1. So if the power is 10%, what's the probability of a type 2 error here? 0.9. The probability of failing to reject the null when the alternative is actually true. That's a pretty high probability of making that error, right? Before we go and look at the last question, one of the things that I want to stop and talk about is finding power. To actually calculate power like the website did takes skills beyond what we cover in this class. So what we are going to focus on is, if I tell you the power, can you tell me the probability of a type 2? If I tell you the probability of a type 2, can you tell me the power? But we are never going to ask you to calculate the power from context. We don't have those skills in this class. Type 1, you should be able to tell me, because you should always be able to tell me what the alpha level is. But the probability of a type 2, I either have to give you the power, or I have to tell you the probability of a type 2 so that you can tell me the power. So far, so good? All right, let's look at the last part of this question. Determine whether each of the following changes would increase or decrease the power of the test. Explain your answers. If we use an alpha of 0.01 instead of an alpha of 0.05, would that increase or decrease the power? Decrease. If you decrease alpha, it makes it harder to reject the null. If it's harder to reject the null, that decreases our power. What about if we used n of 100 instead of n of 25? It's going to increase because, it's going to decrease the variability. So those normal distributions are going to get narrower, which means there's less overlap. That is everything we're covering in this chapter. Additional reading about power, which I would highly recommend doing because we don't have any more like in-class lessons about power. Page 612 to 618 has additional reading about power that I'm going to call it an assignment. I can't force you to do it, but if you don't do it, you're only hurting yourself on your understanding of power in the context of our significance tests. In case you forgot, type 1 and type 2 errors, additional reading, that was pages 592 to 594 on types of errors, and then 612 to 618 on power. Homework is due tomorrow. You guys have the remainder of the class period to work on that.